Section: Introduction. In this section, we introduce our proposed simulated trial and error, SAINT, for learning how to use tools. STE involves two main phases: exploration and exploitation. The exploration phase focuses on trying out different ways of using a tool, observing the outcomes, and learning from both successes and failures. We also proactively imagine possible scenarios for using the tool that are not currently visible. Memory, both short-term and long-term, plays a crucial role in the learning and continued use of tools. To implement STE, we leverage a large language model, LLM, to simulate scenarios for using a tool, interact with the tool through API calls, observe the feedback, and reflect on the results. We use memory mechanisms to enhance the quality of simulated instructions. Short-term memory helps in exploring different possibilities within a single trial, while long-term memory retains past experiences for ongoing learning. During the exploitation phase, we can fine-tune the LLM using examples from the exploration phase or conduct in context learning by referring back to those examples. Our experiments with APIs from Toolbench show that existing LLMs struggle with using tools effectively. For instance, GPT-4 achieves only 60.8% correctness, while Tool LLAMAV2, specifically designed for tool use, reaches 37.3% accuracy. STE significantly enhances the tool use capability of Mistral Instruct 7B, improving correctness to 76.8% and outperforming GPT-4 within context learning. However, incorporating new tools through fine-tuning poses a challenge of catastrophic forgetting, where learning new tools may erase previously acquired skills. We demonstrate that a simple experience replay strategy can help mitigate this issue, allowing the model to learn new tools while retaining existing knowledge. Section Summary. Introduction. Tools are crucial for extending the capabilities of large language models, LLMs, beyond their static knowledge, enabling them to access real-time information, external reasoning, and take significant actions. Current approaches focus on enhancing LLMs with tools through in-context learning, ICL, or fine-tuning, but there is a lack of emphasis on how accurately LLMs utilize trained tools, which is vital for practical applications like financial transactions. To improve tool use, a biologically inspired method called simulated trial and error, SAINT, is proposed, which leverages memory mechanisms to simulate scenarios, interact with tools, and enhance tool use performance in LLMs, demonstrating significant improvements in accuracy compared to existing methods. Section: Exploration. In this section, we explore how we interact with new APIs using a language model, LLM, to learn as much as possible about them within a set budget. Our exploration involves a series of trials, similar to how humans gradually learn to use a new tool. In each trial, based on the API description, we 1. Come up with a likely user query for the API, 2. Try to answer the query by interacting with the API, and 3. Reflect on the trial to guide our future exploration. To ensure the effectiveness of our exploration, we incorporate 3 key design elements into our trials. Firstly, we employ a strategy called React, where the LLM learns from the feedback it receives during execution to improve its own performance. This helps the model correct any errors in its interactions with the API. Secondly, we introduce a short-term memory feature that stores recent exploration experiences to guide future trials. This allows the model to learn from recent successes and failures and explore the API more thoroughly based on past observations. Lastly, we utilize a long-term memory to store distilled trial and error experiences from previous episodes, enabling the LLM to learn progressively over a longer period. This long-term memory helps the model expand its exploration and make advancements across different episodes. Moving on to the exploitation stage, we use the insights gained from the exploration phase to enhance the LLM's ability to use the API effectively through fine-tuning or in-context learning, ICL. Fine-tuning involves focusing on improving the tool use and response generation aspects, while ICL involves incorporating synthesized examples into the LLM's context to enhance its understanding of the API documentation. By filtering and paraphrasing the examples obtained from the exploration phase, we ensure that only valid and relevant examples are used to enhance the LLM's performance. This rigorous filtering process helps us maintain a balance across different APIs and adds linguistic variations to the synthesized tool use examples. In summary, our approach involves a systematic exploration of new APIs followed by leveraging the insights gained to improve the LLM's tool use abilities through fine-tuning and in-context learning strategies. Section Summary. In this section, we explore a method where a large language model, LLM, interacts with new APIs within a budget to learn about them through a series of trials, similar to human learning. The exploration phase includes iterative self-refinement with execution feedback, short-term memory for recent trials, and long-term memory for past experiences to enhance the validity and depth of exploration. In the exploitation stage, trials from exploration are used for fine-tuning or in-context learning to improve the LLM's tool usability, involving filtering, paraphrasing, and incorporating synthesized examples into the model's context. Section: Experimental Setup. In this section, we conducted experiments using various APIs from Toolbench, a repository of real-world APIs. We selected 50 free APIs with low execution latency, covering search engines, domain-specific information-seeking APIs, and problem-solving APIs like Wolfram Alpha and Number Translator. During the exploration stage, we utilized ChatGPT for exploration and paraphrasing, and GPT-4 for final example filtering. Each API went through 15 episodes with 4 trials per episode, resulting in 60 examples before filtering. After filtering, 15 examples per API were randomly chosen for the test set, while the rest were paraphrased into approximately 140 examples, totaling around 7,000 tool use examples. We manually checked and corrected any issues in the test set to ensure quality. We experimented with different models like Llama 2 Chat 7b, 13b, Mistral Instruct 7b, and GPT 3.5 Turbo, GPT-4, comparing their performance with and without STE. Tool LLAMA v2 LLM served as the main baseline, fine-tuned on 126,000 tool use examples synthesized by ChatGPT 3.5 Turbo. For ICL with nearest neighbor demonstration selection, we used a specific model for computing semantic similarity and selected the top 8 examples closest to the test query as in context demonstrations. Due to the length of API documentations exceeding the model's context length, we incorporated an Oracle tool retriever to retrieve similar APIs for Llama 2 with ICL. Models of similar scales were augmented with the same tool retriever for fair comparison when ICL was used for exploitation. Evaluation was based on matching predicted API calls with the ground truth, considering correctness, well-formedness, and API match. The models were assessed on their ability to resolve user queries successfully based on execution results, although this was challenging due to the dynamic nature of the APIs. Results showed that none of the baseline models achieved satisfactory tool use performance. GPT-4 performed the best with an overall correctness rate of 60.8%, while Llama 2 and Mistral had lower performance due to syntactic formatting issues. Despite extensive fine-tuning, Tool LLAMA v2 LLM still underperformed compared to GPT 3.5-4. Indicating that fine-tuning for general tool use was not sufficient for practical deployment. STE proved effective with both ICL and fine-tuning, leading to significant performance improvements across the board. Fine-tuning with suite examples notably enhanced Mistral Instruct 7b's tool use capability, surpassing GPT-4. Overall, STE showed promise in enhancing the tool usability of models and could potentially further improve models like GPT 3.5-4 beyond their current performance levels. Section Summary. In this section, we conduct experiments using a variety of real-world APIs obtained from Toolbench, focusing on free-to-use APIs with low latency. We explore different APIs spanning search engines, domain-specific information seeking, and problem-solving categories. Our evaluation shows that fine-tuning language models, LLMs, with synthetic tool examples, SAINT, significantly improves tool use performance, with notable gains in correctness and well-for-medness metrics, especially for open-source LLMs like Mistral Instruct 7b. This approach enhances the ability of models to select the right tools and predict arguments accurately, surpassing the performance of baseline models like GPT-4 and LLaMA2. Section: Ablation Studies. In this section, we conducted various experiments to analyze the effectiveness of our exploration design. We focused on fine-tuning Llama 2 Chat 7b and examined the impact of different components such as execution feedback, short, long-term memory, and self-reflection. By increasing the number of episodes, we ensured a sufficient number of trials for our analysis. Our results revealed several key findings. 1. Removing execution feedback led to a significant increase in poorly formed examples, where API calls did not adhere to syntax formatting requirements. 2. Both short-term and long-term memory were crucial for successful trial and error processes. 3. Self-reflection played a vital role in maintaining informative long-term memory for exploration. To better understand the benefits of our memory design, we conducted a case study using the forecast_weather API. This study demonstrated that both short-term and long-term memory mechanisms greatly enhanced the diversity and comprehensiveness of exploration. Short-term memory improved specificity and comprehensiveness by enabling the model to explore fine-grained information from the tool effectively. Long-term memory enhanced overall diversity over a longer time span, ensuring that the model explored a broader range of subjects and maintained progress across different episodes. We also analyzed the errors of GPT-4, a highly capable LLM, which achieved an overall correctness of 60.8%. The errors were categorized into 3 types: wrong choice of API, missing, wrong arguments, and hard to evaluate examples. Additionally, we examined the errors of the Mistral Instruct 7b model after fine-tuning, highlighting areas for future improvement such as common sense, world knowledge, language understanding, and grounding issues. Section Summary. In this section, we conducted ablation studies on our exploration design by fine-tuning Llama 2 Chat 7b, focusing on removing execution feedback, short, long-term memory, and self-reflection components. The results revealed that execution feedback is crucial for preventing ill-formed examples, short, long-term memory is essential for effective trial and error, and self-reflection helps maintain informative long-term memory. Additionally, our memory design significantly improved exploration diversity and comprehensiveness, with short-term memory enhancing specificity and long-term memory increasing overall diversity over a long time horizon. Section: Continual Tool Learning. In this section, we delve into continual tool learning. We found that while fine-tuning works better than ICL for using tools, it can lead to reduced flexibility due to catastrophic forgetting. To address this, we looked into continual learning, CL, and discovered that simple rehearsal can suffice for continual tool learning with STE. We divided the tools into 4 batches to mimic continual learning. During each round, we added 10% of tool use examples from previous batches to the replay buffer for rehearsal. To maintain general capabilities beyond tool use, we also included 2,000 random examples from Flan v2 in every training round. We evaluated the model on MMLU and Big Bench Hard, BBH. By using Llama Flan as the base model, we ensured a fair comparison of general capabilities on MMLU and BBH. Our results showed that without rehearsal, the model tended to forget previously learned tools, especially the ones learned earlier. However, rehearsal significantly reduced forgetting, with the CL-trained model performing similarly to Llama FT. The model also retained its general language abilities on MMLU and BBH. Overall, we demonstrated the effectiveness of experience replay in LLM tool learning, showcasing a flexible way to incorporate new tools using the proposed suite method. Moving on to related work, A key focus in NLP research is enhancing models with retrieval search engines to access additional knowledge. There is a growing trend in augmenting LLMs with various tools like program executors, translation and QA models, APIs from developers, and tools tailored for specific environments. Both fine-tuning and ICL are commonly used to equip LLMs with tools. Fine-tuning involves training the LLM on tool-specific examples, while ICL incorporates tool descriptions directly into the context. Our work aims to empower LLMs with stronger tool use abilities, inspired by how humans learn tools through trial and error. Recent studies have shown that LLMs can improve their predictions with feedback, which we leverage in our work to help LLMs learn tools progressively. Furthermore, due to ILM's broad pre-training exposure and advanced generation capabilities, researchers have explored using LLMs for dataset synthesis to reduce the need for human annotations. This synthesized data can enhance models, including LLMs themselves. In the tool learning domain, similar approaches have been taken to synthesize tool-specific data. Our work aligns with this research direction, aiming to enhance the comprehensiveness and diversity of synthesized tool use examples. Additionally, incorporating memory mechanisms in models to gather and utilize experiences dynamically is not a new concept. Recent studies have explored enhancing models with memory of user and environment feedback. Drawing inspiration from these works, we augmented the LLM with short-term and long-term memory to facilitate progressive learning of tools.